In this video, we continue with chapter 3.3, and we are going to take a look at finding determinants of invertible matrices. Let's start with theorem 3.7. So theorem 3.7 says a square matrix is invertible, also known as non-singular, if and only if the determinant of A is not zero. So when we have a if and only if proof, we start by assuming one side of the statement is true and showing it implies the other. And then we start with the other side and show it implies the first side. So on the one hand, we are going to assume if A is invertible. So if A is invertible, then we know A times its inverse equals the identity. That's what it means to be invertible. And then we know from our product of determinants that the product of the determinant of A times the determinant of A inverse is also going to equal the determinant of the identity matrix, which we know is 1 because the identity matrix has 1s on the diagonal. So therefore, we've shown the determinant of A is non-zero. All right, let's go the other direction now. So starting with the assumption that determinant A is non-zero, then we can use Gauss-Jordan elimination to find the reduced row echelon form R. And since R is in reduced row echelon form, it's either got to be the identity matrix or it's going to have at least one row of all zeros. Well, that wouldn't be possible. So then if R had a row of all zeros, then the determinant of R is 0. But then that would make the determinant of A also 0, which contradicts our assumption that the determinant of A is non-zero. So therefore, A must be row equivalent to R, which equals the identity, so A is invertible. So what we're saying is that you can get from row operations from A to R, which is going to have a non-zero determinant. Okay, let's look at theorem 3.8. So this says if A is an invertible matrix, then the determinant of its inverse is 1 over the determinant of A. So we know A times A inverse equals the identity, so it must be that the determinant of A times the determinant of A inverse equals the determinant of the identity, which is 1. Well, then they must be multiplicative inverses, right? So determinant of A is not 0, so A inverse must equal 1 over determinant of A. You could see it this way: determinant of A multiplied by its multiplicative inverse, 1 over the determinant of A equals 1. So we know this must be the determinant of A inverse right here, 1 over A. So this takes us to some equivalent conditions for a non-singular, meaning an invertible matrix that's n by n. So remember, non-singular means invertible. So putting together all the proofs that we've done in the last few videos, we know A is invertible is equivalent to saying AX equals B has a unique solution for every m by 1 column matrix B. That's equivalent to saying AX equals 0 has only the trivial solution, the column matrix for 0. That's equivalent to saying A is row equivalent to the identity matrix, meaning we can get there through row operations. That's equivalent to saying A can be written as a product of elementary matrices. We saw that back in chapter 2. And that's equivalent to what we've most recently seen, that the determinant of A is non-zero. So if you can show that any of these properties are true, the other properties are considered equivalent. Let's work this example. We are going to verify that the determinant of A inverse equals the multiplicative inverse of the determinant of A, or 1 over determinant of A. So here's matrix A, and I'm going to head over to Simpy and do these calculations to verify. So I have to enter matrix A. So the first row of A is 0, 1, 0, 3. Then we've got 1, negative 2, negative 3, 1. Then we've got 0, 0, 2, and negative 2. And then we've got 1, -2, -4, and 1. And we can type A and verify that's our matrix. Looks good. And then let's check to calculate A inverse. So we do A star star -1. The double stars is the exponent command for SIMPy. And so A does have an inverse. Here it is. And so let's check determinant of A is 2. And then the determinant of A inverse, so we put in parentheses A star star -1, is 1/2. So it is 1/2, or the multiplicative inverse. So we have verified this relationship that the determinant of A inverse is 1/determinant of A. So we can say inverse is 1/2, and determinant of A, showed using technology, is 2. So in the next video, we're going to take a look at determinants with transposes.